Hi, good morning, everybody. Welcome to Greenbuild 2014. We hope you've had your coffee this morning. I don't see enough coffee on the table, but we're going to give you an exciting presentation on daylight simulation in 4 architecture firms this morning. Most of the time, architecture firms compete against one another, but the 4 of us are going to give you all of our secrets today. We believe that daylight simulation should be done in all architecture firms. We're all doing it in-house. We think the software is finally to the level where even novice users with a little bit of training, some building science, and a little help can run daylight simulations to make better decisions during the architectural design process. We're not going to show you which buttons to click this morning. We're also not going to go through the evidence that biophilia, connection to the outdoors, and views has positive health effects, positive learning effects, and positive productivity effects. Instead, we've chosen to focus on what the 4 of us feel are 2 of the most important aspects of simulation: asking the questions and framing a simulation response to those questions, and then how our firms are set up to, with infrastructure, to deal with doing simulations. So I'll introduce our group. We've got Joe Mayo from Mahlum. We've got Eddie Santosa from Callison. And we've got Arvinder Dang from SOM. So we'll all be speaking in turn. I'll be going first, and we'll go through the others. So question, how many of you have daylight simulation programs within your firms? Unscientific, about half of you. How many of you actually click the buttons and run the simulations yourselves? So a few less, maybe, but maybe, I don't know, 30%. That's really good. It's more than I expected. So here's a quick snapshot of the 4 firms that we have. You've probably read it by now. We're trying to provide you a good cross-section of how architecture firms have used daylighting simulation within practice. So we have firms from 60 to over 1,000. Some of us use specialists. Some of us just use generalists performing the simulations. But all of us use it to make decisions. So my name is Kjell Anderson. I'm an architect at LMN Architects in Seattle. I'm also an author of Design Energy Simulation for Architects. Came out earlier this year. I've personally found it very freeing to do daylight and other types of simulations. Instead of guessing that a space you're working on might have the right amount of light, not too little, not too much glare, you can actually play with it ahead of time and figure out exactly what, make sure that you're getting exactly what you want to out of it. Play, as with children, leads to an intuitive understanding of daylight. So actually clicking the buttons helps that learning. At LMN, we work on a variety of complex project types: performing arts, convention centers like we're in, higher ed, sports, and mixed use. A lot of our projects are urban, and so rules of thumb don't exactly apply to all of our projects. Since rules of thumb don't apply, simulation is even more important in order to vet kind of more unusual designs, shading, skylights, etc., that are kind of unusual designs that are common to complex building types. With 120 plus employees, we have 5 people dedicated to technology. They're not IT people. They do other types of things. One of the things they do, they create complex parametric designs, and they work with costing exercises and fabricators to make sure that they're realized. They also write scripts to translate between Revit, Rhino, and other software. They operate our quadricopter, which is kind of cool. And they assist with daylight simulations and other types of simulations. So as architects approach daylight simulation as an in-house entity, we have a lot of more power than when consultants perform the daylight simulation. And the reason is we make the decisions. We make a lot of the decisions. If we come up with a better idea by doing a daylight simulation, we can implement it right away. We can talk to the design team 5 minutes later and have it as part of the design. So this is a powerful part of having it in-house. So look around you. Isn't it ironic to talk about daylighting in a space that has no windows or skylights? Most convention centers were built and designed in an era where meeting planners wanted black boxes so you could do cool presentations like this. So I'll tell you a quick story about a convention center, one of the ones that we've gotten some daylight into. This is an exhibit hall in Spokane. And about 10 years ago, we were like, there's a gorgeous view of a river here. Let's put a window in. The client said, I don't know if we want to do that because most exhibitors want dark spaces. We'll probably have to cover it up most of the time. What ended up happening when we talked to them a few years later was exhibitors wanted to be near it. And since the attendees wanted to be near it, the exhibitors really, really wanted to be near it. So when we did an addition last year, we put in a full wall of glazing, and they loved it. Or they will love it when it's done. So this is an even more light-averse space than an exhibit hall. This is a ballroom. So in the Vancouver Convention Center, I don't know how many of you are familiar with that, but we were able to get daylight and views into that space, and it has full blackout capabilities. But that was because of the view. And anecdotally, this is a very successful space. People want to be there. So these connect people to the outdoors, biophilia, but they don't really reduce energy use as significantly as we need to meet the 2030 challenge, and they don't provide the daylight you need for passive survivability. So what we're working on for this project in Columbus that's in DD currently is a tubular skylight system over 100,000 square foot of an exhibit addition that would provide 30-foot candles and be able to turn off the lights for majority of the time. Even though we can black them out, we figure 70% of the time we'll be able to use the daylight and turn off a majority of the lighting systems. So this is kind of the next evolution in that. So this is a floor plan analysis showing contour lines that the manufacturer kind of did for us. But since we do daylight analysis in-house, we were able to kind of vet this and work with them so that we understand what these skylight devices are doing. So as we design projects, we think about what constitutes success for each space, and it's very different for every space. Even within a school building, there might be 2 or so spaces, 10 types of spaces that each have different daylighting requirements. So we think about the question. The question is the most important thing in my mind. Can you turn off or dim electric lights throughout the space? Is glare avoidance critical? What glare control measures are even in the budget? And are there minimum or maximum illuminance levels? Once you have the question, you can get into the software and the infrastructure required for firms to start a daylighting program. We primarily use Diva for daylighting currently. We're a Rhino and Revit-based firm. So Diva provides all the tools we need. It actually combines a lot of the tools we're already using into one package. We also use ComFen, and then Tech Studio is always testing new software and new techniques. So I'm going to talk about a few case studies. So for this project, we had 8 hours to compare 4 masking schemes so we could present them to a client. It was a competition, and we didn't want to spend a whole lot of time on it, but we wanted to quantify performance to some degree. So we chose 3 metrics to compare these office massing layouts. You can see the colors refer to the glazing percentage on each facade based on a really, really conceptual design. We chose a UA value, which is basically the U value of all assemblies multiplied by the area, and then they sum them. And that gives you a basic idea of what cooling and heating loads might be in the space, especially heating loads since it's near Seattle. We chose, we did peak load analysis using ComFen, and then we also did daylighting analysis using spatial daylight autonomy. So spatial daylight autonomy returns the percentage of each floor plate that is adequately daylit, in this case 25-foot candles, during the whole year. So the first 2 metrics balance the third. If you just did daylighting, you would probably end up with a fully glazed building, and the spatial daylight autonomy would tell you that you've got a perfect building. But in fact, you have 100% glazing, and you know you're going to pay penalties in terms of heating and cooling that space. So that's why we threw in the first 2 metrics to balance this daylighting. So we expected A to be the clear winner. We designed it to be such. We thought with a daylight atrium, we could get natural ventilation in there, and we're limiting the glazing on the entire rest of the building because of that. But when you look at the numbers, C actually has a better daylighting autonomy, and it has a fairly decent UA value. So we tried to reconcile this. The decision is complicated by the fact that the atrium in A is a semi-heated space, and it's, in 4 hours, you're not going to be able to model that and compare all the possibilities. But this study basically narrowed it down from 4 options to 2 options, and we were able to proceed from there. And that was the only thing we asked of that particular study. So that one looked at illuminance at it's called the work plane. It's 30 inches above the ground. If you've done daylight simulation, you know that. While the last example looked at those, most people perceive visual balance within a space based on vertical surfaces. You go into your favorite coffee shop, you've got one wall of glazing. On the opposite wall, which you typically have is a bright colored wall, and you have a lot of electric light flooding on there so that you have this visual balance side to side. On this 4-story atrium, we have a single wall of glazing, and we're trying to do approximately the same thing. The question we asked was, how much daylight do we need to provide to light up the balcony rails on the opposite side so that we don't have too much of a visual contrast between them? 30-to-1 is a ratio that can be used to approximate visual balance within a space. So if it's about 1,000-foot candles just inside the window, and it's about 30 or 40 or 50-foot candles of illuminance on the balcony railings, we would achieve success, and that's about what we did. So we didn't have a quantifiable answer. We had an answer where we achieved a certain amount of visual balance that we were looking for. So it's important to calibrate any of your daylighting simulations to something you understand and something you know. When we did an office remodel last year, we had the amazing opportunity to go out with light meters every day in our space and calibrate our simulations to exactly match reality. That's why I'm covering this particular space. And then we moved in afterwards, and of course we've done thermal comfort studies and visual studies. We were actually commissioning the blind system ourselves so that it goes up and down at the exact right times. The first study we looked at is a light shelf that you see here in this section. We used Diva on this one, and you can see we have the image on the top and the image on the bottom. Image on the top, no light shelf. We have the image on the bottom. This uses a metric called useful daylight illuminance. UDI is, they call it a Goldilocks metric. It's not too little, not too much. It's just right. So we're looking for 10-foot candles to about 200-foot candles here. What we can see is with the light shelf, it doesn't really improve the areas around the perimeter where we have overlighting and potentially glare. And we can look at this a different way that kind of shows that even better. This is UDI looking at the upper graphic is too much light, and the lower graphic is underlit areas. We have very few underlit areas, and in fact, the entire perimeter is overlit. So one thing we did from this was move all the desks away from the exterior walls, or exterior windows, 4 feet, and that really helped. Another thing we did with this same metric was essentially we were able to then just move the desks around so that they achieve daylight. We're not looking for daylight in the abstract. We're looking for daylight at the work surfaces. So by moving the desks around, we were able to increase the daylight autonomy at the work surfaces, which is where we want it. And we did that in Photoshop, which was pretty cool. But one thing we didn't cover in those was blinds. And if you've ever worked on trying to extract daylight energy savings, or energy savings from daylight, from dimming your systems, one of the big issues is whether you have automatic or manual blinds. Manual blinds tend to be put down and stay down for days or even weeks. And so you get no daylight harvesting during those periods of time. So this is a Diva simulation using DaySim that shows blind schedules with automatic operations on the top and manual operations on the bottom. And there's a fairly significant difference in terms of the amount of energy savings you could harvest out of lighting systems. So based on these, we've saved about 50% of the energy use from the previous lighting system. So for my last case study, museums, this is going to be a museum. It was an armory, now a museum. It's on South Lake Union in Seattle. Museums have a love-hate relationship with daylight. They love the fact that it renders everything well, but they hate the fact that it deteriorates their artifacts. They often exclude it so they can preserve their collections. Most simulation software takes data from the weather file to create a luminance map, the middle image, of the sky dome, and then that essentially projects light onto your geometry, which creates daylight simulations. Reverse ray tracing means it's in the opposite direction, but essentially this is what happens. What we did for this one, we wanted to be able to take into account the context, the trees, any reflections from the lake, etc. So what we did is we take HDR photographs, which I think many of you are probably familiar with, of the entire sky dome. Well, HDR photographs are luminance images. So we're able to composite these into a luminance map of the sky that essentially replicated the middle image here. Except it was very specific to our site, very specific to the context, the trees, the water, everything around. And we're able to use that as a luminance map for our daylight simulations. So this allowed us to do not only the bottom left image, which is a typical luminance type study where you look for glare within a space, but it also allowed us to do photorealistic, photometrically accurate renderings, which are the ones on the right. Those aren't Photoshop images. Those are actual images using the HDR sky that we created. Normally, when you look out of a rendering, you see the HDR sky, the CIE sky that you use to do the rendering. But in this case, we're actually seeing the HDR images that are projecting light into this space. One of the advantages of this is we could then test out blind systems and see, based on the relative luminance levels, what type of blind system would provide the right balance between preserving artifacts and allowing views to the Space Needle and the lake. So back to the simulation process. One of the ways that we've found to be successful with getting our tech studio and our simulation into projects is by setting up sessions at the beginning of every design phase where we brainstorm questions with the project team that we can answer using simulation. Sometimes they generate questions on their own, and sometimes they need to be prompted, which is why we set those up. And our biggest challenge is usually getting the right person to run the right simulation at the right time. If you're a week early, design has changed and your results are no longer valid. If you are a week late in getting the right person to the right project, the decision's already been made and there's no going back. I'd also like to mention our blog. Later today is going to be a posting. We've tested several daylighting softwares over the last several months, and we are about to post that later today based on comparing them for usability as well as comparative accuracy. So with that, thank you, and I am going to turn it over to Eddie Santosa.
Thank you very much, Jill. After Jill make a good presentation about the daylight at LMN, I would like to share what we do at Callison. We are a 1,000-person architecture firm, and we do different type of building, from specialty retail to workplace environment. We have 10 different offices around the world, from Seattle to Shanghai in China. In our performance simulation team, we have people in Seattle, Mexico City, and Shanghai. We consist of 14 people with one specialist, which is me, and we train people from architecture studio to do energy simulation and daylight simulation. This is one of the session training that we have. In terms of daylight simulation, we put it in a bigger context of performance modeling. This is our typical approach that we want to implement ideally in all the projects. As you can see, it started with establishing energy target to delivering energy modeling for the lead compliance. If you see the fifth row, it's actually a daylight analysis. Ideally, we would like to do it in early design, at least until the SD stage. So you have opportunity to play with your meshing and the shape of your building. In our daylight simulation, this is our typical process. There is two major software that we typically use, a DView for our climate analysis, and a DIFA for Rhino for our daylight analysis. For architecture firm, I think for the people to learn daylight simulation, I think the most important one is to understanding daylight metrics and the sky model. This is the key to do a daylight simulation. After we talk about the background in our company and how we set up the group, I would like to share two interesting case studies. Both are interesting because we couple between energy performance and daylight performance in the space. The first case study is a retail project in Dubai. This is our initial design sketch from our design team. As you can see, our goal is to focus to provide the daylight in the corridor space and the food court area. As you can see, it's actually we provide a good daylight or design scheme by putting the skylight on the east side and the north side of the corridor. If you follow the rule of thumb, it's the best design. However, we test with our energy simulation. Our current design actually performs above 200 kilowatt hour per square meters. We are also experimenting with a different type of scheme by eliminating all the skylight, putting only the 15% of area of the skylight and 30%. And we can see our initial design actually not perform really good. Other scheme perform below 190 kilowatt hour per square feet. After we assess the daylight energy, we want to see how's the daylight in the space, especially in the corridor. We play with 4 different options in the beginning. If you see, the option 1 is actually our initial design sketch. In option 2, 3, and 4, we introducing different type of shading device and light monitors. For example, for the option 3, we have a 15-degree shading device and continuous light monitors. We test our daylight simulation at June 21st, 1 o'clock, because it's one of the peak load in the building. We use a standard of 200 lux to 500 lux. 200 lux is the minimum IS luminance recommendation for the corridor space for the retail building. So this is a result of our simulation. The first image actually showing the rendering or the luminance level. The second one, the second column showing the illuminance level. Our target is showing around the blue color, which around 200 to 500 lux. You can see our initial design is showing a problem also in a daylight. We achieved more than 30,000 lux on the space. So you can see the correlation between bad building and the energy performance and the daylight. In our option 2, it's getting closer with our target. It's 750 and 300 lux. And this is our option 3 and 4. It's getting better and better in terms of like illuminance level that we want to achieve. After several iterations, actually we choose this option with a clerestory window and a skylight with a diffuse type of glass. You can see the illuminance level, we can achieve the target around 300 and 400 lux. After you see the evolution of illuminance, you can see when starting we have really high illuminance level, but in the end we can achieve the targeted illuminance target, which is around 200 to 500 lux. We also use this approach in another space, in the food court area. I will just go briefly in the food court area. This is our initial design and comparison with our improved design. As you can see, in our initial design, we have 2,000 lux, and in our improved design, we have 500 lux. What we do to make it better? There is a 3 strategy that we change in the building. The glass that facing south part, we change it with make additional perforated metal in the outside and a fritted glass in the inside. We also introduce a diffuse glass in the small skylight in the ceiling. After we talk about the retail space in Dubai, I would like to share a project in Abu Dhabi. It's a triangle-shaped office tower. In here, our goal is to optimize the facade and using the energy and the daylight simulation to make sure that we have low energy building and a good performance in terms of daylight. In here, we use energy simulation as our assessment tool. Probably most of you familiar with EQuest. EQuest is mostly people use for lead compliance or code compliance purposes. In this case, we're comparing 4 different schemes. Our initial design is a sleek tower building without any shading device. You can see the performance of EUI that's showing 100.3, and also we can also see the performance of daylight from how many percentage of electrical lighting that we save. In this scheme, we have saving of 48%. We introduce shading B and D in the option 1, which is a vertical shading and acrid shading device. This is each shading that we apply in the facade. And you can see the energy performance is dropping, which is getting better. But we compromise a little bit in daylight performance. The more energy saving from a daylight, from the electrical lighting, it means that the more daylight that we introduce to the space. We also test the perforated metal by adding a shell in the building. And you can see we compromise a lot in the performance of daylight, although in the energy performance we're getting better. We only introduce a daylight and saving the energy around 35%. Our preferred option is actually the last one, which is we balance both. In terms of energy, we're not the best one, but we also still get a lot of daylight and view for the building. In the eQuest, our typical result is from LS-I. So if you don't have a daylight simulation and you have a lead project, definitely you have an energy modeler. So you can ask your energy model to test the daylight also, the performance in the building in each zone area. In here is showing the electrical lighting usage saving in a year. It's showing a month and also showing the every hour saving. You can also learn about the illuminance level in space. Every zoning, they will have a report that you can pull out and see the illuminance level in the building. So it's very handy if you don't have a daylight consultant in your building. This is not probably the most accurate compared the radio city or ray trace simulation, but it's good enough to drive your design, to make a decision what type of design that's better for your building. In conclusion, we can see the daylight simulation is no longer only for LEED compliance, but it's also for making a better design, high-performance building, and comfortable space. We also see the rule of thumb is no longer valid. It's no longer sufficient to address the needs of sustainable design. Thank you. And I will hand out to Joe.
Thanks, Eddie. Hi, my name is Joe Mayo. I work for Mahlum, an architecture firm with about 60 employees and 2 offices, one in Seattle and one in Portland, Oregon. I have to say that I'm not a daylighting expert, and no one in our office is a daylighting expert. With about 30 employees in each office, we don't really have the amount of projects in the office or the resources to devote a full-time staff member to daylighting. But despite this fact, I think we've been able to achieve a very high level of success in daylight design without having any bona fide experts on staff. So what I wanted to talk to you today about is how we've been able to achieve this, a little bit of history of the firm, where we started, where we moved to, and how digital simulation tools have helped us in the process. A milestone project for us was the Seminar 2 building at the Evergreen State College, which opened in 2004. The project was important for us because it marked the first collaboration we had with the IDL, the Integrated Design Lab, which is a research group at the University of Washington that specializes in energy analysis and daylight simulation. By collaborating with the IDL, we were able to integrate a variety of daylight strategies across what we term the building's 5 facades. And in doing so, it also achieved the first LEED Gold rating for an academic building in Washington State. Although the LEED Gold rating was important to us, what was actually more important to us was by working with the IDL, it created set a precedent and create a workflow in our office where we would integrate daylight analysis into our architectural design process. So moving forward, every project in the office actually would integrate daylight analysis into our architectural design. And we first started out doing this by building a physical model and taking it to the Integrated Design Lab and testing it on their Heliodon artificial sky, testing a variety of different strategies to really optimize the daylighting. And in this way, I think we trained many staff members at Mahlum by building the model and going to the lab and testing it. And it also created an atmosphere in the office where we were constantly just talking about daylighting and discussing what good daylighting meant. Over the years, we worked with the IDL many times on many different projects, a lot of them K-12 schools, where we were really trying to do daylighting at no added cost. So it was really a great pressure. And also by doing this, I think we established what I would call a really intuitive understanding of good daylighting, how to do good daylighting. So a few years ago, we decided that rather than relying so much on out-of-house experts, we thought we could be more nimble in the design process by actually integrating digital simulation tools into our workflow. So we started out this process by actually hiring a recent architectural grad from the University of Washington who had worked in the integrated design lab for a few years during college. And he came to our office and helped kind of set up really early on the tools we were using, train some of the people in our office, and then that just moved outward. And many other people in each office have been trained since then. And he also really served as a person to talk to validate our results, which can be sometimes the most challenging part. So a few of the workflows that we've looked at in our office and I'll discuss today are using Ecotect, using ComFin, using Revit, daylight illuminance in the cloud, and then again, also touching base again on the just physical modeling and using the integrated design lab. So this is a middle school in Issaquah, Washington. It's currently in the design phase, just started construction documents. It's a different building for us because tight site constraints put us into a difficult situation where we had to orient the building with the classrooms facing east and west, which is a different design problem for us where we typically orient all the classrooms facing north and south. So using digital simulation tools really helped us quantify the problem and come up with a good solution to the problem. And so here we started out using Ecotect. And if you're not familiar with Ecotect, our strategy for using the software is we're doing all of our architectural modeling and documentation in Revit. But exporting a Revit model into Ecotect doesn't really work, so we're remodeling geometry in SketchUp, exporting that into Ecotect, applying daylighting glazing materials in Ecotect, and then using the Radiance plugin to do the analysis. So it's a number of steps, and it's definitely not a seamless process, and there's many problems that can happen along the way, but once you get good at it, I think it's a very useful tool. And so, as Chell was saying, we always want to start out with asking a question. So the question here that we started with was creating daylight equity. Because of zoning height limit, the building could only be 30 feet tall, and programmatic elements on the ground floor are really really compressing the upper level classrooms. And so the upper level classrooms had less window wall to work with, so we wanted to ask the question, how can we create a level of equity between the upper and lower level classrooms? And so to do this, we really just started out doing a variety of really quick comparative studies. Using SketchUp and Ecotect, you can do the comparative models and simulations really fast. You can do all these in probably a day. Our first look was adding clerestory windows to the upper level classrooms to drive daylight deeper. Adding skylights is just a very simple design move to create a more even distribution of light across the space. And then also moving a little bit into detailing and seeing how far we could push the window wall to the underside of structure to get every possible inch out of the window wall we could. And with these different strategies, we were able to present them to the client. The client was able to make an informed decision based on their needs and the budget of the project. And while the amount of daylight in the room was one problem, another problem was certainly with east and west facing classrooms, direct sun penetration and glare into the classrooms. So to understand this problem, we actually just analyzed a typical classroom at a variety of times during the day and times of the year. It's a process we'd probably want to automate a little bit more rather than just checking various times throughout the year. But what we did find was kind of surprising for the west-facing classrooms that for the majority of the year, because class is dismissed around 2 or 3 p.m., there was really only a problem with direct sunlight in the winter months, and the rest of the year, there's only an hour or two of direct sun in the classrooms. So we started looking at some different exterior shading devices that were optimized for the winter months. And so the question here we were asking is we knew that in times of direct sun, on the view window, the roller shade would be deployed, but on the daylight window, we wanted to leave that open to allow natural light into the classroom, even at times of direct sun penetration. So we were trying to optimize the daylight exterior shading device here. I'm not going to spend too much time on that because we had a value engineering session midway through design development that eliminated all of our exterior shading, which I'm sure many of you are familiar with. So at that point, we decided that, well, we knew we were only going to be able to use interior shading devices, so at that point, we decided that using a different software package would actually make us more nimble in the amount of iterative studies that we could do. So we switched to ComFin5, which is a program developed by Lawrence Berkeley National Labs. And it has a lot of really great out-of-the-box interior shading devices. So roller shades where you can choose a different color, the amount of openness, which are, to create those materials in Ecotect, you have to have your own material definition for those, which is a little bit out of the expertise of our office. So this actually allowed us to do the simulations we wanted to do. And also can do model Venetian louver blinds at different angles. You can set them to be automated. So it just really has a lot of great tools. So here what we're looking at is kind of a baseline option. This is a plan, looking at the typical classroom and plan. So having all dark roller shades on both the view and daylight window, having a light roller shade on view and daylight windows, or having a combination of a dark roller shade on the view window and a light roller shade on the daylight window. And from this analysis, it looked like the light roller shade was really providing the best even distribution and amount of daylighting in the classroom. So this seemed like a pretty interesting choice for us. ComFin5 is also able to analyze glare, so the next step we wanted to do was look at how a light roller shade was actually affecting the glare. And so looking at those exact same options, as we would expect, the dark roller shade pretty much eliminates glare, but the light roller shade toward the end of the day actually produced a pretty glary environment. So the combination of a light roller shade only on the daylight window helped mitigate the majority of glare in the classroom and was still providing a good amount of daylight into the classroom. So this helped us quantify the situation. This is the direction we moved on to. We've certainly made some changes along the way, but without digital simulation tools, I don't think we could have come to this conclusion. So really quickly, I also want to touch base on an elementary school in Mercer Island, which is also in the design phase, just also starting construction documents. Here, since we're doing all of our modeling in Revit, it really makes sense if we can do daylight analysis in the same program that we're doing our modeling, so we don't have to spend time remodeling and exporting and applying different materials. And so Revit has proved useful for that. This image on the left is looking at two identical classrooms in plan. The only difference is the bottom classroom has an additional window placed in it. So like Ecotech, we're using these as comparative studies to see what making changes to the model, how that affects the overall daylight. And even though we have specified an overcast sky for this model, which is the dominant sky condition for the typical school year in the Pacific Northwest, it looks like there's direct sun coming into our classroom. So we're not sure that, we don't really understand that the analysis that Revit is giving back to us right now, so we have a little bit of question about that, but I think overall it's going to be a useful tool as it continues to be tweaked. This is where I think it really pays off, is for these large spaces or full building analysis that would take a long time to remodel. You can really study the space quickly, and because it uses a cloud for the rendering, they come back within a couple minutes. So this is a gymnasium space where we've oriented the skylights in one particular direction. And so just to study how daylight would be affected, we tried switching the orientation of the skylights. And just looking at the two, you can see that the image on the right has much more natural light washing the walls. And so just intuitively, we could see very quickly that this was a better orientation for the skylight. So this is the direction that we moved on to. Revit is also able to do full building daylight analysis with their plugin. And it's kind of expensive in terms of cloud credits, but I think it's a pretty useful tool. And it can also export schedules, which is really nice. You can do your lead documentation right inside of Revit. And so hopefully at the end I can touch base on a little bit more of what I think are the pros and cons of each of these software packages. But right now I'm going to hand it off to Arvinder.
Good morning. My name is Arvinder Dang. I work as a part of the high-performance design group at Skidmore and Merrill. We're an integrated multidisciplinary design practice, offices all across the world, a lot of work currently international in Middle East and Asia. What I wanted to actually share is more our design methodology, a little bit how we're set up, but how our process has evolved related to daylighting over the last year. And the scales that we work with is very different. So on one side, we have an urban planning group doing city design or going into existing cities and designing these. And on the other hand, we have an interiors group. So the kind of analysis we do or the tools we employ have to really address the scales and the design parameters we're really trying to analyze for that, relevant to that scale. Not each tool is good for the particular analysis at hand. So I'll touch a little bit on how we've been trying to do urban analysis or using radiation analysis to inform urban frameworks. So we're set up as different studios, a big number of architectural studios. We have a core engineering practice, both MEP and structural in-house. And I actually started my career, I'm an architect by background, but started my career doing energy modeling, and joined an engineering firm. So I'm at the midst of this all, and this high-performance specialist group lies at the midst of all these studios within our office, trying to provide analytical services, be it daylighting, be it energy simulation modeling, airflow analysis, comfort studies, and now some amount of infrastructure conceptual design as well. So the process really is, currently we've been looking at simulation, whether it's daylighting, energy, comfort, in separate packages, There's different simulations are done by different members sometimes, having experts in different fields. But then the results are collated. We look at them together to see how one decision, a daylighting feature or an element in our architectural design is informing energy, but simultaneously, how is it impacting daylight? But what's really important to understand for us is the interrelationships. Too much daylight or a lot of direct radiation, as you saw in some of the case studies that were presented, could lead to really high HVAC loads, but more importantly, really impact the comfort that is perceived by the occupants. On the other hand, really good diffuse lighting can really reduce electrical energy and energy consumption overall while enhancing comfort. So initially, our process was very similar to what Joe presented. We used to use Ecotect. Models were created. Sometimes the input to the geometry was really complicated, and it really slowed our process. Soon we realized we were using the Radiance engine always to do our analysis, but we realized it was becoming really prohibitive in terms of time, in terms of even, especially related to curved geometries. We do a lot of super tall high-rise towers, and not always is our geometry rectilinear. Floors change, a lot of curved surfaces, and often we realized, that we couldn't keep up with the design iterations that the architects were making. A lot of innovative tools have emerged in the last few years. Most of these are actually plugins to Rhino, but there's Grasshopper, which allows for a lot of parametric analysis. Diva is a tool that we've been using a lot. We really like it because it allows us to look at an annual daylight as opposed to just instance in time. Ladybug, Urban Daylight. And all these are plugins for Rhino. A lot of our geometry is created in Rhino, or it can be imported into Rhino. And then depending on whether we want to do an urban analysis, we'd use Urban Daylight and Diva, or if we want to do a more specific building scale analysis, we'd use Diva and eval glare with it to do some glare assessments. And now we're trying to test Honeybee. So not going further into tools, but to share with you some of the examples on an urban scale. This is actually a project in Jakarta that we were working on. And early on, when we were trying to inform the design framework, we wanted to look at what the blocks should be like, what should be the massing, how does that really determine the radiation levels that fall both on the facades and on the ground plane. And so we looked at different block typologies, got into detail, and looked specifically at ground level radiation and facade level radiation. And we really quickly realized that our design wasn't performing. The urban comfort would be not there in these blocks because there is so much radiation that people would, the outdoor realm is going to make people uncomfortable. So what is an alternate way we could look at this? So we investigated alternate building typologies or alternate building massing scenarios. We introduced a diagonal street here. And we also varied the podium heights across And we realized that because the sun, we're near the equator and the sun is on the northern hemisphere, by varying the heights of the buildings, the podium level buildings, and also adding a few towers on the north side, we could now shade the urban realm more and make the space comfortable, or it would be perceived as comfortable given that people are walking in the shade. Simultaneously, we also did airflow studies and looked at wind velocities at human height to see how that impacted comfort. So, as I said, lots of new tools have emerged, and the fact that we can now do parametric analysis, we can also extend this to informing how our street framework or what the width of our streets is in an urban design project. Here, we looked at urban daylight and in conjunction with Grasshopper, and we tested multiple street width options to see how that impacted daylight autonomy as well as radiation levels on the facade. So we tested 3 options here, a 20-meter, 30-meter, a 25-meter, and a 30-meter option. And when moving from a 20-meter to a 30-meter, a 25-meter street width, we were able to increase the daylight levels in the building from 34% to about 55% in terms of how better daylight. But any further increase in the street width really didn't help. The impact was really marginal. So that was kind of an optimal size that we determined. And this analysis could be further extended to, test different building typologies, what the orientation of the building is. Do you introduce a courtyard or not introduce a courtyard? What's the aspect ratio? And help inform your large-scale master plans or urban framework. We extended that even to determine what the optimal size of a courtyard would be in terms of an aspect ratio. And a lot of this analysis was actually done fairly quickly. It was, I think, a matter of less than a day that all this analysis was done. And it is the use of these parametric tools and the fact that the geometry can be created really fast, and it is a plug-in tool into the same tool that we're doing the architectural geometry, really fast, makes the process fast. So jumping scales here from an urban framework or urban analysis to what you would do specifically at a building level. This is a project, it's a training facility for Roche Diagnostics in Indianapolis. It's mainly a showroom training facility for medical equipment lab, like repair of that. And so what you see in the central rendering there is a super lab space that is central to the building, and on the upper floors, flanked on both sides, is the seminar rooms. So I'll walk you through the entire process. Like really early on in concept, we were brought in and they said, we have these different massing scenarios we want to look at. We want to look at a one-story larger super lab space, a two-story space similar with a larger super lab but attached to a building, the existing building, and then a third one which was a standalone two-story, a smaller, a different scale super lab space. And we ran some quick point-in-time daylight analysis, and then we mapped the daylighting profile across the section to determine the kind of quality of light that you would get within the space, the illuminance levels. And very quickly, we were able to assess that our third option, which was a standalone option, provided much more uniform light. The levels of light were close to the levels we needed, which is the red dotted line you see across there. And we were able to get light in more number of spaces. As we moved into schematic design, we started testing different options for the skylight for the Superlab space. We tested 7 different scenarios. Our architect started with a really large skylight over the Superlab space, which was a clear skylight. We knew that this is not going to perform, but we wanted to still test it to prove it. And then we introduced a translucent skylight, a super large. We tried modeling multiple skylights as an alternate. And then we also looked at clear story and roof monitor options. And the graph you see on the left here is those illuminance readings being mapped across the section of the Roche building. And you see the first 2 options, the red and the blue line there. They're really off the charts. The blue dotted line at the bottom is really 300 lux level line that you need within the space. And really early on, we were able to rule out that you can't do such a big, large volume with that big a skylight. Simultaneously, we also tested for glare as well as did some false color renderings for the space to look at the quality of light. And here we were testing, using eval glare, there's an index called daylight glare probability, where if you establish a view angle, you can determine how much glare an occupant would perceive from that viewpoint. And the first two options there, again, had intolerable or really high values with intolerable glare, and the roof monitor option was the option we proceeded with. We moved into DD, and we started fine-tuning what this roof monitor would be like. We started with the rectilinear geometry, and then we said, it's probably we can make this better. And we looked at a sawtooth monitor and a scoop monitor. And both those options indicated higher levels of daylight in the space. And in the end, the scoop monitor did perform better than the sawtooth, but for cost reasons, in the end, we proceeded with the sawtooth monitor, as well as the visual aesthetics desired were more rectilinear in nature. And along the way, we were also looking at daylight autonomy and useful daylight illuminance that Shell touched on early on, which is like an annual climate metric for the entire year. And we also looked at it for specific space types. I'm looking at my timer here, and time is running faster than I would like. So I'm going to go fast because I really want to share an interesting study that I have right after here. This is a similar process we use to optimize the facade, similar to the skylight option. And we were looking at different overhang depths, as well as louver options on the exterior of the facade. And the graph on the right really shows a more interior perimeter, that in the interior space where daylight levels don't change much when you look at it in an interior. But closer to the facade, when you see the two graphs on the left and the right, is where you see the maximum variation and the peaking in the daylight levels. So this is something unique that we tried out. I don't know if anybody has looked into this before. A very interesting study. We always look at daylighting with respect to, how does an architectural element or a device inform lighting quality within a space? Do we have a light shelf? How would that impact it? What is the glazing? How is that going to impact the daylight? A roof monitor, building form. We never think about landscape. How would landscape really impact the daylight in this space? And here, it just so happened that the landscape architect, when he was doing his design and we were in coordination meetings, he said, we want to put a row of honey locust trees adjacent to the facade, like 7 meters away from the facade. We're like, okay, that's going to impact the daylight. So we wanted to go test what is that ideal distance from the facade that the trees should be placed, but also what height. We had to make some assumptions. What height would you allow the tree to grow? The honey locust tree is really it's a deciduous tree, so it sheds its leaves in the winter, and basically it's got really fine leaves which allow dapple light to flow through it, to move through it. So we had to also look at how can we really model this leaf geometry or the properties of the leaf to determine the quality of light that is in the space. So I had a really talented guy who was working with me at that time. Got to get credit to him. Martin Brennan actually came up with a methodology to model this. He took the leaf structure or the tree structure in Photoshop, mapped it into Illustrator, and then actually created a rhino model. He mapped it over a hemisphere to create this tree object. And now DIVA has within it an ability to create shading profiles, which are generally applied to shades, but you can switch on and off a certain shade device. So this tree was really modeled like a shade device, where the leaves were put off in the winter and they came on in the summer. And then we tested the tree spacing for different daylight autonomy and different models, looking at different spacing types for the trees. Of course, as we moved from a 20-meter to a 30-meter tree spacing, the daylight autonomy within the space increased, but there was also an increase in a little glare in the space. And as you move further on to a 40-meter span distance, the daylight autonomy increased more. So there was a fine balance, and we chose to go with a 30-feet option, trying to optimize between more daylight and less glare. And what you see here is really a visualization on the left at a certain viewpoint. This is an annual glare probability done for an option without trees and with trees. The image, the graph on the top, really, the red indicates the amount of glare that you would have within the space if there was no shading, but you didn't have any trees either. And in the second option, just by adding those trees close to the facade, we were really able to eliminate a lot of glare. So just want to end here with this little animation, and hopefully it will run. Apparently, I think it's right again. It was running before, I guess. Not working now. But this was really an animation showing through the day how the trees impact the daylighting or the luminance levels within the space. And this is just an image you can see later at about 5 o'clock, where you do see that the luminance levels are much lower in the space. Thank you. And I'll open up for questions now for the entire team.
Microphone somewhere in here. Anybody have any questions?
I had a quick question over here. So it seems like a lot of different models and simulations are really providing a lot of data, a lot of pretty colored graphs, and I'm just curious if, in a couple instances, you guys mentioned, this was cut because of budget region, this one didn't work because of the geometry, even though it was more effective. I guess my question is, what have been the strongest cases that you've been able to make with these models that actually holds enough ground to say, like, yes, this is something that will really make the design more rich?
For me, I guess my mic's on. For me, a lot of it, if you can get it down to thermal comfort within a space, comfort is actually important. Thermal comfort, but also visual comfort. It's interesting. Some clients are really into utility savings because they're going to own it for 30 years, and some clients are going to sell it, and an 18-month payback is not long enough for them. You craft your story for each client, and you design for every client. You might want a certain material for the facade, and they don't like that, and even though you study it for 30 hours, they still reject that. You might study a daylight option for 30 hours, and they reject that as well. So it's just like anything else in the architecture process. It's actually so different for every client that I don't know that I have any whole lot of generalizations.
Yeah, I would say that working a lot with schools, we want to push daylighting just to create the best learning environment that we possibly can. So, that's really the angle that we take, where it's really for the occupants of the space. And when we're using daylight simulation tools, we're only going into really the technical metrics on a few spaces in the building, like the typical classroom, and then using more so quantitative in a few number of spaces, and then qualitative in a larger number of spaces. And like Chell said, actually the client on the Issaquah middle school basically wouldn't accept clear stories or skylights, which were providing the best amount of daylighting. So it was really on a case-by-case basis what you're able to do. But I think the graphics and the simulation, being able to present that is a huge benefit, not only to the client but within the firm when you're discussing the actual design goals.
I think as similar with what Jel and Joe mentioned, The thing is also we need to see from the financial point of view. If you talk with the client, the thing that I didn't really discuss, but when you do a better design on an envelope, typically the big impact is not in the energy. The energy impact is probably like 3 to 10%. But the big impact is actually in your peak load. The peak load will affect your mechanical system. So the assessment need to be like integral in overall your design. It's not only daylight, but also your energy and your mechanical design, because it's correlate each other. It's not only one standalone when you approach to the client.
I'd also like to add that most of the time we do daylight simulation, it's to make our designs better. So we use it as an internal tool, and most of the daylight designs we do, we don't present to clients. We just compare 5 options and choose the best one and just proceed as if, we're good designers. We chose the best option. We also might study, 3 floor plan layouts and decide on the best one as well. So in a lot of cases with daylighting, you don't have to convince the client unless it is adding a skylight or a large cost item. Another question?
Yes. Hi, I'm Ben Cole with Innovative Design from Raleigh, North Carolina. Thanks for your presentation. A couple of questions and comments on your presentations for most of you all. Now, you are using a lot of software that just came out to the market very recently, but have you ever verified your software accuracy with the measurement and verification in the spaces after it's built? And because we use a lot of projects, we use DaySim, and we've done that verification about 6 months of the data actually collecting from the actual space, and compared to the software using the same the weather data of that 6 months. So I was wondering if you've done like that study in Diva or Confen or other software you use. And also, when you do the simulation, of course, you assume the interior finishes and furniture, the light reflectivity. And also, have you gone back to the spaces and actually take a look at that those finishes, colors, and furniture, and then just calibrate your software back into the space? That's my question.
In terms of like validation, I think it's a great question. For like a daylight autonomy is tricky because you need a whole year or a long period of assessment. In myself, I did some verification for like a single point on time. I think I published a paper last year about the lead building and the performance on thermal and visual. I think it went out really well. Radiance, I think, is pretty well validated. I mean, that's still tricky. I mean, for they get a good validation on daylight autonomy. That's the thing that we love to do it, but unfortunately, sometimes we don't have opportunity to work with the client once the project done. The second question regarding the furniture. Typically, in the early, we try to do a daylight simulation before we make a decision with interior design. So we tell our interior design, this is our assumption. If you change, let me know so we can adjust. Definitely, the interior design have a lot of impact on the daylight, but we usually already understand what kind of color they're looking for. We usually ask what kind of range of color they're looking for. If you have a brighter color than we expected, we usually adjust on a VLT number on the glass. So kind of like balance. So that's why we need to carry out across the design process, not only in early, after that you stop.
Just to add to Eddie's point, we hope to do more daylight validation with our actual designs, doing physical measurements. For the Roche project, at least, we're really hoping to do it. The project's under construction. It's been harder and harder to do it. We're doing, in lieu of trying to test, we've been trying to test our own office space at SOM to do physical measurements and then model the same space in Diva and see how it compares. But these software are already tested and validated, as Eddie mentioned. They're all using the Radiance engines. These validations have been done before. I think it's more validating our designs and how we are designing them later with post-occupancy surveys and post-occupancy data is something we're hoping to get more of.
We have some cool graphics we'd like to show. A survey we did. If you put our presentation back up for just a second, go to the very last 2 slides. If we can, oh, yay! Now we've got the animation. After this, anyway, we did a survey of 16 architecture firms that do daylight analysis and what software they use, and we thought it was kind of interesting what the answers were. We can get past this slide. Or not. Basically, Revit, everybody wants to use Revit for daylighting, and a few packages are coming online for that. Oh, there we are. This is the last one. And Diva is also increasing in popularity. Ecotect is going down a little bit. IESVE is going down by one. There's only 16 architecture firms. But Confen, Saphira, and Open Studio is going up. Open Studio is connecting with Mostafa and Honeybee and Ladybug and Butterfly, so they're going to back end that software. So a lot of people probably are going to start using Open Studio, even if they don't know right now that they will soon be using it.
Yep, the session's wrapping up now. We'll have a new session coming in. I know a few folks had some questions that you'd wanted to ask these speakers, so I'd ask that if you guys ask your questions outside the session room, maybe if they can stick around, that would be great. Thank you all.
Thank you.
Thank you so much.